To speak. So yeah, indeed the title of my talk will be the simplification of caustics. And so the following will be the plan. I want to start by just giving a little bit of background on singularities of Lagrangian and Legendrian fronts, just to set the notation and introduce the various elements from the theory of singularities that we will need. Then I'm going to state the H principle for their simplification. After that, I want to give a couple of applications. So one will be just a simple example, just spheres. For spheres, the homotopy theory is simple enough that we can actually compute the homotopical obstruction, at least in the even dimensional case, and so it's not a conditional statement. You actually get some absolute statement for the simplification. And then I want to talk about Legendrian knots in R3. Again, in R3, the Lagrangian Grassmannian is a circle, so we understand the homotopy theory of the circle well enough that we can just give concrete results. And finally, I want to give an idea of the proof. So this is our roadmap. OK, so let me start. So what is our setup? M will be either a 2n dimensional symplectic manifold, or a 2n plus 1 dimensional contact manifold. And all of the results that I will talk about today hold both for symplectic and for contact manifold, so I will just use M interchangeably throughout the talk. And now I have affiliation F of M by Lagrangian or Legendrian leaves. So maybe you should think that F is induced by some Lagrangian or Legendrian fibration. So for example, we could have M be the cotangent bundle of the base, and then the projection is the usual projection, or we could have M be the one jet bundle, and then this projection is the front projection. Or this is just B cross R. So these are the sort of examples that we care about, and actually these are always local models for Lagrangian or Legendrian foliations. There's no local invariance. And then what is the object of interest? A singularity of tangency of a Lagrangian or Legendrian embedding F from an n-dimensional manifold L into M is a point. Actually, let me write it Q, such that at this point we have a tangency. Okay. So this is the object of interest. This is what we want to simplify, and maybe I will make a remark that the singularities of tangency of the embedding with respect to the foliation, the locus of such is denoted by sigma. It's a subset of L. In the particular case in which the foliation is given by a Lagrangian fibration, this is the same as the singularity set of the smooth map, which is the composition of F with pi. And this is what we usually call the front, the Lagrangian or Legendrian front of the embedding. And so simplifying the singularities of tangency is the same as simplifying the singularities of the front as a smooth map. Okay, any questions so far? Now I need to introduce some elements from from the theory of singularities. So let me remind you of the Tom Boardman hierarchy. So we can stratify the singularity locus in the following way. Sigma k is the set of points where the dimension of that intersection is exactly k. Okay, and now generically, for a generic f, each of these is a open submanifold of codimension k plus 1 over 2. And there's a general model, which is that the sigma 1 singularities, these are understandable in a way that I will make precise in a moment. And sigma k for k greater than 2, there's no hope. To be more precise, there are infinitely many local models which occur generically. If the dimension goes high enough, there's moduli of non-equivalent singularities. So these are non-classifiable in some very strong way. Like one would hope, if one wants to prove some theorem, one will just make the local calculation with every local model. That's just not going to happen. It's just too hard. Generically, the singularities are terrible, and so one has to give up. On the other hand, the sigma 1 type singularities are quite understandable. Let me be a little bit more precise. You can further stratify the sigma 1 locus as a flag. And then each of these, let me denote a string of 1s of length n by 1 to the n. And then each of these guys has a unique local model. It has a unique local model, and moreover, we have some pretty good geometric understanding of what it looks like. So let me give some examples.
Is that sigma, is it like a universal object, or?
It's a universal object. So it lives in some jet space, and then sigma is like the pullback of that universal sigma that lives in the jet space. And so the universal sigma is stratified in these ways, and then it pulls back to some stratification, and then under certain transversality conditions, the stratification on L is nice.
Is it, but it's finite. Capital sigma, that sigma is finite dimensional, or?
Yeah, this will be of codimension k plus 1 over 2 and L. Yeah. Okay. So let me talk first about the simplest possible singularity that exists, which is the sigma 1 zerofold. So you have your contact space, and then you have something like this. And then if you project to the front projection, you get the good old cusp. If you project down to the Lagrangian projection, you get this fold, and if you project all the way down to just the Lagrangian base, then you get something like this. So this is just a map x goes to x squared. So this is really, really understandable. It's just a good old fold, and then in higher dimensions, you will have a fold times Rn minus 1. So this is fold times Rn minus 1. And this is a semi-cubical cusp in the front projection. So the sigma 1 zerofold, we understand very explicitly. There's no complication. I'm going to give one more example, which is sigma 1, 1, 0. This is the pleat. And now I don't have enough dimensions to draw on the board, but OK, I'll do what I can. So in the front projection, this roughly looks like this. And now if I want to draw the Lagrangian projection, I'm going to have to lose one coordinate. Let me lose the Q2 coordinate. And then this is going to look, let's see. So it looks like this. And this is the pleat. And then what is important to understand is that the pleat is the birth-death of two cusps. or the birth-death of two folds. So what is sigma 1, 1, 0? It is the birth-death of two sigma 1, 0 singularities. What is sigma 1, 1, 0? It is the birth-death of two pleats. What is the next one? It is the birth-death of the previous one, etc., etc.
You said you lost the Q2 coordinate, but you put Q2 on that diagram.
Sorry, I lost P2. Thank you.
Okay.
Yeah.
Okay.
Yeah. And what you should think of as P2 is sort of the error as I'm evolving. So what I'm doing here is I'm thinking of this as a one-parameter family of fronts, which is the usual Reidemeister 1 move. And then if I draw the corresponding one-parameter family in the Lagrangian projection, I get something like this. And so this is what I've drawn. But of course, I have another P2 coordinate, which is what happens in the direction of the parameter. And this one I'm not drawing. But this one is not. No, this is the front projection.
Is the front projection always the AN?
Excuse me?
Is the front projection always just the AN singularity?
No.
So in the Suster cases, it's like the swallowtail of the AN singularity.
The front projection always the AN singularity. I'm not sure, but I don't see why that would be. It could be. It could be. I haven't thought about it.
From two pictures.
Yeah, yeah. In any case, this is somehow the point that these are very understandable. We have local formulas. These were discovered by Moran, and we have a good geometric understanding. We actually have techniques for manipulating singularities of type sigma 1, which we call sigma 2 non-singular. This is surgery techniques. And so sigma 1 singularities, we're in good shape. We can understand sigma 2 singularities and beyond, there's no hope. I think that's all that I wanted to say. Yeah. And so I want to now.
Sorry,
Yeah, absolutely. Uh-huh.
So we took capital sigma, we stratified by the dimension of this intersection.
Uh-huh.
What are we stratifying by to get sigma 1, 1, sigma 3?
Okay.
Is there some other dimension
Okay.
to count there?
Sure. So let me
Something like Schubert cells or something?
So this is a sigma 1, 0 locus. Now consider the kernel. Okay, consider the kernel of this map. The kernel is a line field like this, which is transverse at all points. Consider here, I have this map. Now it projects with some singularities. And so consider now the kernel. The kernel is now transverse at all points except at the single sigma 1, 1, 0 pleat. And so what you actually do is you look at this kernel, which is one-dimensional, and at the points at which it's transverse, you have sigma 1, 0. At the point at which it's tangent, you have sigma 1, 1, 0. Now, restrict yourself to the sigma 1, 1, 0 locus. Where it's transverse, you get sigma 1, 1, 0. Where it's tangent, you get sigma 1, 1, 1, 0, and so on and so forth.
Thank you.
Mm-hmm. Of course, this is really a bad definition because it only works in the generic case, and so you actually want to define these things universally in the jet space, and that's what Boardman did. So that's a better definition. Okay. In general, defining these things universally in the jet space.
Sigma 2, is it somewhere in the middle, more understandable?
No, not understandable. No hope. No hope. It's just terrible. Excuse me?
So initially you have the Lagrangian knowledge on the loop, so it seems that you're going to have dimensions of uniformity. But now for this theorem, it will just happen in the jet spaces, so you're always 2n plus 1?
No. This is all in the Lagrangian. This is all in L.
But then you have 3 coordinates, and now you have 5 coordinates.
Excuse me, where do I have 3 and where do I have 5?
So from what you were describing here, so you have 3 coordinates.
Yeah, so this is a contact manifold. This is a Lagrangian. This is a symplectic manifold. This is the front projection, and yeah, I'm doing both cases simultaneously because I think it's instructive to think of both simultaneously. All of these have.
So
Lagrangian and Legendrian analogs. If you take the Legendrian lift of the Lagrangian one, you get the Legendrian version.
So this hierarchy is for Legendre and Lagrangian?
Yeah. I mean, this hierarchy works for smooth maps. That codimension formula is a little bit messed up because you have to, there's a shift because of generating functions, but this stratification exists for singularities of smooth maps. In particular, it exists for
Okay, but this description with local models, now you're doing something about.
yes, that's right. Actually, so this local model here, this is just a smooth object, and then these are kind of the contact and symplectic manifestations.
Okay.
You seem unhappy.
Yeah, maybe you're used to presenting it to a more expert audience, but the dimension story I find pretty confusing. Because here you have something, you made it sound like you had something that was three-dimensional inherently in the top picture, and then you're just projecting it to explain to us what it looks like. And there you have the five-dimensional thing, you're projecting it in a much different ways to tell us what it looks like. Is that right?
This is a two-dimensional Lagrangian or Legendrian in a 4 or 5-dimensional symplectic or contact manifold. Yeah.
Okay.
And then in higher dimensions, you multiply this picture by Rn.
Yeah.
Yeah. Yeah. More questions? Okay. So now I want to simplify these. And why? Well, there's a lot of reasons. For instance, Ekholm's method of Morse flow trees only works when the only singularities are sigma 1, 0 folds. If you're trying to do family floor, then and imagine these are your fibers, then the fact that I only have sigma 1, 0 folds means that the chain level generators appear in Morse depth bifurcations. There's combinatorial methods that have been exploited for the study of one-dimensional Legendrians that one could hope could be extended to other cases, but we just haven't been able to, because then you would have to do the combinatorics for all these singularity models, and that's just no hope. And so simplifying these singularities is a thing that maybe we'd like to do, and so now I'm going to explain how to do it. But the first thing to mention is that there exists a homotopy theoretic obstruction. To simplifying the caustics. And by caustic, I just mean a singularity of the front. Okay, and let me just show the most stupid example, which is suppose that these cycles, which you can show are cycles, the boundary has dimension strictly more than one less. So these give you some cycles. And so of course, if these classes are not zero, then you can't remove them. Okay, so this is the stupidest cohomological obstruction. There's much subtler homotopy theoretic obstructions. And so if these obstructions are not zero, then I'm sorry, like bad luck. You need that singularity. But what you could hope for is that if the homotopy theoretic obstruction vanishes, then I can genuinely simplify the singularities. And so that's the H principle, and that's the theorem.
Would we change the map or the?
By Hamiltonian isotopy, by an ambient Hamiltonian isotopy.
So the foliation should be changed.
No.
The map.
I will state the theorem precisely in a second. So first, let me explain how to access this homotopy theoretic information. And so what you have to do is you have to decouple the embedding from the tangential information associated to the map. So let me.
Is it obvious that this class is independent of the Hamiltonian isotopy class? I mean, that there's a well-defined cohomology class in this. Is it obvious?
Yes. I mean, I don't know if it's obvious. If you believe that these things are defined in the jet space, then it is, because it's just the pullback of some class defined in jet space. And if you don't, then I agree there's some work to do.
Yeah, probably it's unclear to me how you define them in jet space and
Yeah.
put them back. So.
These are some characteristic classes. For example, sigma 1 is the good old Maslov class, which is some class that's universally defined, and you pull it back, and that gives you your Maslov class.
So that sigma 1 does not have, does that sigma 1 have to do with that sigma Archie 1
Uh-huh. Yeah. This is Poincare dual to the Maslov class that you know and love. I mean, the Z lift, the integral lift of this one. these are co-oriented only for odd k. Okay, so let me define the following object. So tangential rotation of a Lagrangian or Legendre embedding f from L to M is a compactly supported deformation I'll explain the notation in a moment. And here t is going to run between 0 and 1, such that I'm starting with the Gauss map, and I'm going to ask that this deformation always covers f, and here this is the Lagrangian Grassmannian. So in the symplectic case, this is the Grassmannian of all n-dimensional Lagrangian subspaces of the tangent space to M. And in the contact case, this is the Grassmannian of all Lagrangian subspaces of the contact distribution. So if you imagine this being your embedding, and so here is your Gauss map. To every point I associate the Lagrangian plane that is tangent to the image, then with a tangential rotation, I'm allowed to now homotope these tangent planes in a way that it's totally uncoupled from the underlying embedding. So I'm separating the information that is encoded in the map with the tangential information encoded in the Gauss map.
What do you mean by compactly supported?
I mean that this GT is equal to G0 outside of a compact set. This is important because at the end of the day, I want things to be induced by an ambient Hamiltonian isotopy, and exact homotopies of Lagrangians are only, I can only guarantee that they're induced by Hamiltonian isotopies when they're compactly supported. But I'm getting ahead of myself. So the following observation is easy. If there exists phi t isotopy such that, let's say just best case scenario, such that phi1 of f is transverse to the foliation f, then there exists a GT tangential rotation such that G1 is transverse to f. This is not immediately obvious, but it's actually not so bad. Okay. So the converse is almost true. So there's various statements. Let me start with the one in which I have a tangential rotation which ends up being genuinely transverse to the foliation. So this is precisely the statement that there is no homotopy theoretic obstruction to simplifying the singularities. Okay. Then the conclusion is that there exists a Hamiltonian isotopy, compactly supported, so that all of your favorite J homomorphic invariants are preserved, such that the singularities of tangency of the wiggled embedding with respect to f are all sigma 1, 0 folds. Okay. So this is the H principle in its simplest form, and it says that this necessary condition is almost sufficient up to the fold. Any questions about the statement? let me make some remarks.
So now we're just doing symplectic manifolds in the problem?
No, contact also.
You still call it a Hamiltonian?
I still call it a Hamiltonian isotopy. I mean, I agree.
That's fine.
Yeah, thank you. Thank you for the clarification. Yeah, I mean, and I will call like all homotopies exact, even in the contact case, just because otherwise I have to repeat each statement twice, and it's a pain. Yeah.
So, but in the contact case, you're not doing strict contact homomorphism.
Maybe it would be better if I say there exists a homotopy of Lagrangian or Legendrian embeddings, such that at time 1, all the singularities of tangency are sigma 1, 0 folds, and then in the Lagrangian case, I moreover demand that the homotopy is exact. Okay. So I want to make some remarks. So the first one is that I actually have quite a lot more control over the singularity locus, at least in the source.
Can I ask one question?
Sure.
Is the I mean, you said we have this observation. You said this is part of converse.
Yeah.
But is the converse of the theorem true? Also, I mean, is that obvious? Is that even
I will get to that.
Oh, okay.
I will get to that. Yeah.
Okay, sure.
Yeah. There's a lot more you can say, but this is like the yeah. So more precisely, this is going to be a disjoint union of so-called double folds. And double folds just means that you have a pair of folds on concentric spheres. So in the front projection, they look like two copies of this. So this is a half double fold. And also maybe nested. And by nested, I mean that maybe it looks something like this. Okay. So and these are homotopically trivial. Observe that I can formally cancel this fold against this fold. And if you don't see that, then take my word for it. But these are the only singularities that you will get. This is what the proof gives you. Second remark is that these are rigid. So double folds are rigid, or exhibit rigidity. Maybe it's better. If double folds didn't exhibit rigidity, I could prove the nearby Lagrangian conjecture in a bunch of cases, which I cannot. And so, and there's various authors that have done some work on their rigidity, and really these double folds, you cannot just get rid of them. And more is true if you look at the combinatorial structure of the image of the double folds. All of the rigidity is encoded there. All of the J invariants morally should be encoded in the image of these caustics, which are just a bunch of immersed spheres in the front projection.
Can you understand their count?
Excuse me?
Can you understand their count? How many they are?
No. Potentially, I could have the proof gives you no bound on the number of nestings. I could have an arbitrarily long nesting of double folds inside double folds inside double folds inside double folds. In the case of smooth maps, you can use surgery to always absorb it into one existing double fold. But for fronts, this is just not the case. Yeah, I don't have anything more to say about that. But I mean, this is definitely stuff worth exploring. I just haven't thought about it a lot.
Can you describe again this double fold?
Sure.
I'm not sure I see what's denoted.
Okay, so in the source, these are two concentric, contractible, codimension 1 spheres, along which F has folds, so sigma 1, 0, and which moreover they have opposite Maslov co-orientations. So this is to distinguish this picture from, say, this picture, in which these two folds have the same Maslov co-orientation. So this is not the right picture. It is this picture in which the folds have opposite Maslov co-orientation. And here I'm drawing a half of a double fold. So you would have these two concentric spheres in your manifold. And one has one Maslov co-orientation, one has the other. And so that you can formally cancel them. And so they're very simple in the source. But like I say, in the target, they might be very complicated. And a lot of information is contained in the way that they're immersed in the target. Okay. Next comment, this H principle is full in the sense that it exists in C0 close, relative, and parametric forms. So I can demand that this Hamiltonian isotopy is C0 small. I can demand that if my tangential homotopy is fixed near a closed set, then my Hamiltonian isotopy does nothing near that closed set. And I can demand that if I have a bunch of Lagrangian embeddings, Legendrian embeddings parametrized by any space, then, and if I have a bunch of tangential rotations parametrized by that same space, such that this conclusion is true, then I get a family of Hamiltonian isotopies parametrized by that same space such that the conclusion holds. Moreover, it also holds in relative form with respect to the parameter space. So if that was confusing, then please feel free to ignore it. I don't want to phrase it precisely just because it'll take 3 boards, but know that this is a parametric H principle. So whatever parametric statement should hold does hold. Okay, that's all the remarks that I wanted to say for this version. Okay, so next I want to address a question that was before. So next, suppose that there exists a tangential rotation such that G1 is sigma 2 non-singular. And let me remind you what that means. That just means that the dimension of G1 of Q capped with T intersected with this has always dimension less than 2. Okay. So then there exists phi Hamiltonian isotopy such that V1 is sigma 2 non-singular. So because the double fold, which is what is produced by the technique, is already sigma 2 non-singular, for sigma 2 I can just completely have a complete converse. Okay, maybe I should say an obvious necessary condition for the conclusion to hold is that there exists a tangential rotation which ends up being sigma 2 non-singular, and so this theorem says that the converse is true. Some remarks. A lot more is true. Okay, a lot more is true. So like I said, if G1 is sigma 2 non-singular, then the singularity locus, you can define the singularity locus for a formal thing in the same way that you defined it before. It's just a set of points at which the tangent plane given by G1, the Lagrangian plane given by G1 intersects the plane that is tangent to the foliation F. And it turns out that when this is sigma 2 non-singular, in the same way you can stratify this singularity locus And you can stratify it by folds and pleats and etc. all the way down. And moreover, you get certain co-orientation data, which I don't want to be precise about, but there's some additional data that, together with this flag, completely characterizes the singularity locus, completely characterizes the germ in a neighborhood of sigma. And you call the flag plus data the chain of singularities. This was defined by Eliashberg in his thesis for the case of smooth maps. And then you can actually show the following. You can show an H principle, or rather, so there is an H principle, which is also proved in the same paper. There is an H principle for the prescription of singularities. Any homotopically admissible chain. And this is also up to double folds. So let me explain what I mean. Suppose that I have any Lagrangian or Legendrian embedding. And now suppose that I have a tangential rotation that at time 1 is sigma 2 non-singular. Then, by a Hamiltonian isotopy, I can deform my embedding such that my deformed embedding is A, sigma 2 non-singular, and B, its sigma 1 chain of singularities is isotopic to the 1 of G1, together with the co-orientation data, and maybe it has some additional double folds. I mean, almost certainly it will have some additional double folds. So not only do you have an H principle for sigma 2 non-singular embeddings, but also you can prescribe any homotopically allowable chain. And this kind of answers the question about the actual converse to this statement. Okay, and this is actually useful in applications. Any questions about that? So there's a lot of technicalities here, and I'm sorry if the precise nature of these statements is not clear. The truth is there are a lot of definitions and technicalities, and so the only thing that I'm trying to communicate is that basically anything that is homotopically allowable can be realized, and then if you actually want to see what that looks like in the detail, then I'm happy to talk after. I should make another remark, which that this was Entoff's thesis, another student of Eliashberg, assuming that 1, F already to start with is sigma 2 non-singular, and 2, that GT is sigma 2 non-singular for all t. And then, with these two assumptions, you can use a surgery technique. And so this is a very nice thesis. It is the first H principle for the simplification of caustics, and he was able to prove some results about two-dimensional Lagrangians. The problem is that these conditions are not generic if the dimension of the Lagrangian or Legendrian is at least 3. And so to get started using the surgery technique, you need to get rid of the sigma 2 singularities. And there was no known H principle to this day that got rid of the sigma 2 singularities. And so that really constrained the potential applications of the H principle. Even for two-dimensional Lagrangians, one-parametric families will generically develop higher singularities, and even for one-dimensional Legendrians, two-parametric families would develop higher singularities. So it really restricted the domain of the H principle for low-dimensional, low-parametric settings. And now this other H principle, which uses a different technique, completely gets rid of that constraint. So that's the new mileage we get. Okay. So I mean, there's some more things that you can say, but this is a sampling of the general theorems that one can prove of this nature. And so next, I would like to actually show you that there's some concrete calculations that one can make. Because in the H principle, people always tell you, oh, well, if the homotopical obstruction vanishes, then you can go to the races. But OK, who's going to compute that homotopical obstruction? OK, no one said that algebraic topology is easy. And so, I just want to argue that in a lot of cases, one can get something concrete out of this. Any questions before I turn to applications? OK, well, let S be a Lagrangian or Legendrian sphere. Again, here's something easy that you can check, which is that if S is Hamiltonian isotopic to a sphere with only sigma 1, 0 folds, then consider the vector bundle, which is consider the distribution. Let's think of it as a Lagrangian distribution, which is the restriction of the distribution tangent to the foliation to the sphere. And so a necessary condition for this simplification to be possible is that this is stably trivial as a real vector bundle. Okay. So corollary, when n is even, this condition is also sufficient. Okay, so this is a concrete statement. So for Lagrangian spheres, at least in the even dimensional case, a necessary and sufficient condition for the simplification of singularities to be possible is that this distribution that is tangent to the foliation is stably trivial. Okay. Maybe I'll make some remarks. So V is automatically stably trivial for all even n not congruent to 2 mod 8. So actually, there's no assumption except if n is congruent to 2 mod 8. And the reason is that the complexification of V is trivial. And so by Bott periodicity, it's not hard to show that, that this implies that V is automatically stably trivial. Okay. Second remark that I want to make is that, so maybe it's true for all spheres inside the cotangent bundle of the standard sphere. Indeed, we know that in this case, the foliation, which is the cotangent fibers, is stably trivial. So that's a thing. Another thing that I wanted to say is the first case in which the simplification of singularities is not possible. So if V is the Hopf bundle on S2, a single sigma 110 pleat is unavoidable. Okay, so this is the first case in which you really need higher singularity. I mean, it's not a higher singularity, right? It's just a plate. Like, it's actually not that bad. But this is just to say that actually the simplification is not always possible. Sometimes there is life. Okay. For n odd, we can give a necessary and sufficient condition for the simplification in terms of the class determined by the distribution of Lagrangian planes, which is an element of pi n of the homogeneous space un mod on, which is the Lagrangian Grassmannian. So when n is even, we can think of the image of this element under the long exact sequence in homotopy associated to this vibration. And because pi n of un is 0, actually this injects. And so it's sufficient to consider the v as a real vector bundle. And so this is why for even n, we're able to give the necessary and sufficient condition just in terms of the real vector bundle. But for n odd, pi n of un is not 0, and so it's not that simple. Does that make sense? This is the clutching function. You should think of this as the clutching function corresponding to the vector bundle underlying the distribution v. Another remark. So another remark. OK, so now I've argued that even in the odd dimensional case, we can give a necessary and sufficient condition in terms of v as an element of pi n of lambda n. But of course, pi n of lambda n is understood. And what I mean by that is we have explicit generators. And so I actually haven't done this work, but here's a program that should be possible. Look at each of these generators. Figure out what singularities they have. OK, those are all the singularities of spheres with some double folds. I don't know what singularities come up. Maybe they're really bad. Maybe they're really OK. I'm not sure. But in any case, you just need to look at these explicit generators, figure out what singularities they have, and then the H principle should tell you that those are the only singularities that will appear for any Lagrangian or Legendrian sphere up to Hamiltonian isotopy. And maybe the last comment is that for general L, of course, things are not so simple as in the case of a sphere, but one can hope to develop an obstruction theory. To compute the homotopical obstruction. I also haven't done this work, but I believe this should be possible. I'm not sure how general a statement one will get, or whether one really will have to work case by case. But this is precisely the sort of problem that obstruction theory was developed for. So that definitely seems to be the next natural step if one would want to compute these homotopy theoretic obstructions in any generality. OK, so that concludes the example of the spheres. Next, I want to talk about a generalization of the Reidemeister theorem for Legendrian knots in R3. But I'll pause for questions about this application for spheres. OK. So next, I want you to consider the space of Legendrian knots in the standard contact R3. OK. And inside, I want to consider the space of Legendrian knots with mild singularities. here I'm thinking of R3 as the jet space, the one jet space of R with R, and it comes equipped with a natural projection, which is the front projection. And so I'm thinking of the foliations as the fiber of the front projection, which are tangent to the p directions. And so I want to consider the subspace of L consisting of those knots with mild singularities. So the singularities consist of two kinds. Ones are folds, and the others are embryos. So let me explain. So a fold is what we already know. It looks like a cusp. In the front projection, it looks like a it looks like a parabola in the Lagrangian projection. And then what is an embryo? So these are generic for individual knots. And what I mean is that if I take an individual knot, generically it will only have fold singularities. And what are embryos? Embryos are the good old Reidemeister 1 moves. So let me draw the move. So what's the deal? I don't have, maybe it's actually better if I draw it. Let's see. Like that. Something like this. And the front projection here, I can draw it, but it's a little more singular. And there I have the two cusps. And so this is an embryo right here. It is the moment of birth-death of two cusps. And this is the Reidemeister 1. And the Reidemeister theorem tells you that a one-parametric family of Legendrian knots can be, generically only has these two types of singularities. And so the question is, how does the topology of M relate to that of L? This is not clear, because a priori, a high parametric family of Legendrian knots will have terrible singularities. And so it's not clear how the topology of the subspace of knots with mild singularities relates to the topology of the space of all knots. Okay? And now there's a stupid problem, which is that pi 2 of L relative to M is not 0. This is a stupid problem in the sense that it's stupid. So consider, I don't want to say this. Consider a one-parametric family of knots, which, OK, so sigma 1, 0 singularities occur generically for single knots. Sigma 1, 1, 0 singularities occur generically for one-parametric families of knots. Sigma 1, 1, 1, 0 occurs generically for two-parametric families of knots. So take a disk where I only have a single sigma 1, 1, 1, 0 singularity in the center. And then this gives you a non-trivial element here. So, OK, that's too bad. But this is stupid in the sense that I can fix it. And so one can define a space D, which consists of pairs F comma D, where D is a discrete decoration of the mild singularities of a knot in M. Okay, so I mean, knots in M have mild singularities. They just have cusps and embryos. And I don't have time to define exactly what this decoration is, but there is some discrete data that one can assign in different ways to such mild singularities. And now the map, which forgets which forgets the decoration and then includes the knot into L, gives a map from this space of pairs to L. This is surjective on pi 0. There are many ways to decorate. But it's not injective, since again there are many ways to decorate and the different decorations might be not equivalent. But here's the corollary, that D to L is a weak homotopy equivalence on each connected component. So this should be thought of as an Igusa type theorem, which says that higher singularities are necessary. Generically, for one parametric families, you only need folds and embryos. And now this is saying, well, actually, it's all you need. That is all you need. Given a map here by some, this is the usual thing. Given any family of knots parametrized by a disk of arbitrary dimension, such that on the boundary the singularities are mild, and moreover I have some compatible choice of decorations, which does not occur in that case, then up to homotopy I can lift this back here. And this follows from the parametric H principle. So this uses the full strength of the relative parametric H principle, and yeah, so this is some Reidemeister theorem, and this is where there might be some hope of extending some of the combinatorial methods used so far for the isotopy problem of Legendrian knots, maybe to apply them to higher families and maybe get some grasp on the homotopy type of the space of Legendrian knots. Okay, so I'm running out of time, so I want to very quickly say just a couple of things about the technique of the proof. But I will stop for questions about the second application.
Can you give an idea of what these decorations are?
Yeah. So it's going to be essentially a configuration space of points and intervals. And the points will be assigned to cusps, and the intervals will be assigned to pairs of cusps with opposite Maslov coorientations. And when I undergo a Reidemeister 1 move, 2 pairs of cusps will be born, and I will assign an interval that kind of keeps them together, paired for all life. And then they go around, but they're still paired by this interval, and then at some point they die, and the interval shrinks to a point. So it's some configuration space of points and intervals that keeps tracks of the singularities. It's not hard to define. It would just take me more than 3 minutes, which I don't have. Yeah.
But still it's discrete.
It's discrete. It's discrete.
I mean, this interval is kept track by the fact that your nodes are oriented.
Yeah. OK, so proof of the H principle. So the proof goes like this. So here's my foliation. Here's my Lagrangian knot. Actually, let me draw it with some terrible singularities. So maybe it's like this. So what is the input to the theorem? The input to the theorem is a tangential rotation, which at time 1 is transverse. So this is the input. And then what I do is I use a wrinkling technique. And I'm able to construct a wrinkled object which is transverse to the foliation also. And then after I have this wrinkled object, I regularize this wrinkled object and get something that only has folds.
What is the wrinkled object?
Yeah. I understand. I mean, again, I really would like to spend some more time on this, but I don't have. So I will simply say the following. This is, so loose Legendrians and wrinkled Lagrangian embeddings come from applying the wrinkled embeddings theorem to the front projection. This comes from applying the wrinkled embeddings theorem to the ambient manifold. So what this looks like in the Lagrangian is something like, so I'm out of time. I think I started 5 minutes late. I don't know if I should stop or 1 more minute.
Yeah, we can.
Okay. So let me just explain the distinction, because I think it's important. My wrinkled objects look like this in the Lagrangian projection, and in the front projection, they look like this. Where now these are semi-quintic cusps, and these are semi-cubic. And when I regularize, I get something that is nice and smooth. And in the front projection, I get something which is also nice and smooth. Okay, I mean, okay, it has semi-cubic cusps, but as we know, semi-cubic cusps are perfectly smooth things in the front projection. And so, and maybe I should contrast this with the picture for loose Legendrians or for wrinkled Legendrians, which is something like this. Here I'm in the front projection, and a wrinkled Legendrian has a wrinkle in the front projection, which in the Lagrangian projection looks something like this. So it's like not an embedding at all. So as you can see, so these are wrinkled Legendrians, Murphy. And these are, yeah, I'm really going to apologize for the notation. These are wrinkled Lagrangian and Legendre embeddings. It's very hard. I mean, either I called them something else or I wasn't consistent historically, because these are called wrinkled embeddings, and then you make them Lagrangian. I don't know. Yeah, it's the notation is terrible. But in any case, the point is that in Murphy's thesis, she applied the wrinkled embeddings theorem to the front projection. And here, what I'm doing is I'm applying the wrinkled embeddings theorem in the manifold itself. And so you end up with these semi-quintic objects in the front projection. And the point is that you have this theorem, which is that given GT a tangential rotation of F, a Lagrangian or Legendrian embedding, there exists Ft an exact homotopy of wrinkled Lagrangian or Legendrian embeddings, wrinkled in my sense, such that the Gauss map of these wrinkled Lagrangian embeddings, which exists, because look, there's a tangent plane at every point, is C0 close to GT. And so these wrinkled objects satisfy a C0 approximation result for tangential rotations, and this is exactly what happens in this step. I have my G1, and then I use the flexibility inherent in wrinkled Lagrangian and Legendrian embeddings to C0 approximate G1. And so, of course, if G1 was transverse to F, then any C0 approximation will also be transverse to F. And then once I'm transverse to the foliation, I regularize in this way, and I end up with something that only has folds. OK, fine, it has a pleat here, but I can remove it with a surgery. It's not too bad. And that is basically the whole proof. OK, so I'll stop here.